Okay, so good day everyone, and you're welcome to another episode of the BJ's Physics Classroom. This section of the Physics Classroom is going to deal with Newton's laws of motion and collision, momentum. This topic is selected from the Form 1 syllabus because I know that some of our colleague Form 1s are at home. So if you're also a continuing student, a Form 2 student that hasn't done Newton's laws of motion and momentum, it's also good for you. Okay, so let's begin. So we start with the Newton's laws of motion. So Isaac Newton gave us 3 laws that govern motion. So we look at them one by one. Newton's first law of motion. The first law of motion, as propounded by Newton, states that a body at rest will continue to be at rest, or a body in a uniform motion will continue to be in the uniform motion unless it is acted upon by an external force. What is the meaning of this? So suppose let's look at this scenario. If I throw this object up, if I throw this, according to Newton's first law of motion, if I throw the pen up, the pen is supposed to continue to go up and not come down unless it is acted upon by an external force. So if this pen goes up and comes down, it means that a certain force is acted upon it, external force is acted upon it, and that is what is causing it to come to rest in space and then eventually coming down. That force is the force of gravity. So another interpretation of the Newton's first law, like I put this pen down here. According to the law, this pen is supposed to be here 100 years if no external force happens to it, if no external force is acted on it. And it is true. If no external force acts on this pen, the pen will continue to be here 100 years, which is true. So according to that law, we also call that law the law of inertia. So Newton's laws of motion. Newton's laws of motion. So we're dealing with the first law. Now, the first law, we also call it the law of inertia. The law of inertia. The law of inertia states that a body at rest or a body in a uniform motion will continue to be in that motion unless it is acted upon by an external force. So the same law is what we refer to as the Newton's first law of motion. So what is inertia? You see, inertia is basically the state of a body. Let me put it in a simple terms like that. It's the state of a body. So as I sit down like this, I'm in a certain state of inertia. So according to Newton's first law, if I put this pen on this, the pen will continue to be here. Look at what is going to happen to the pen. See, when I suddenly pull this, I suddenly pull the book towards my side, the pen feels reluctant to change its state. What state of that? State of uniform, state of rest. So every object at rest feels reluctant to change its state when an external force is acted on it. That reluctancy of the object to change its state is what we refer to as inertia. So when we say inertia of a body, it is the reluctance, we define it as the reluctancy of a body to change its state. We can have state of rest, you can have state of uniform motion, state of time, state of direction. We have so many types of inertia, but at your level, you're only supposed to know inertia of time, inertia of rest, an inertia of uniform motion. So this pen is in a state of inertia, which is inertia of rest. So when I suddenly pull this one, the pen continues to be there. You understand that? Because the pen feels reluctant to change its state. So the pen is trying to obey the law of inertia. That's why when I pull the book, the pen continues to be there. That is the Newton's first law of motion. What are some of the applications of the Newton's first law of motion? Now, you see that passengers are provided with seat belts, or drivers are provided with seat belts when they are driving to wear. This is very important, my brother and sister. It's very important. The seat belt is there to protect you, the user of the car. The car can have an accident at any point in time. When an accident occurs and you are on your seat belt, if even the car somersaults, you will still continue to be at where you are until the car finally stops. Then you are safe. Yes. Then you are safe. So why the seat belt? Listen to this. Let's suppose that the car collides with another body. Or let's say you are in a car. The car hasn't collided yet. You are in a car. Then all of a sudden the driver applies the brakes of the car. Sure, like that. So the car comes to a stop. But your body feels reluctant to change its state. What state was that? The state of uniform motion that the body was engaged in previously. When the car was in motion, your body was engaged in a state of uniform motion. So the body felt reluctant to change that state when the car suddenly comes to rest. So you realize that when the driver applies the brake, you are thrown forward because your body still wants to continue to be in that state. That is one of the applications of the Newton's first law of motion. So passengers in the car are provided with seatbelts so that when the car collides, you are not thrown forward. You are not thrown out of the car. If you don't take care and the car collides, you come out of the windscreen, and then the unfortunate may happen. God forbid that it happens. Good. So that is one application of Newton's first law of motion. Another application of the Newton's first law of motion is the fact that, when you are in the car and you throw an object outside the car, you throw an object outside through the window, the object hit the ground and ran and followed the car. You understand that? Because the car was in a state of the object was in a state of uniform motion whilst it was in the car. So when you throw it outside, when it hit the ground, it feels reluctant to change that state. So it will still have to continue in that uniform motion. You get the concept? Another application is what we call knee jerking or neck jerking. Sometimes, let's say you are watching TV, you are focused on a Chelsea match, and then all of a sudden your friend comes, because he knows that you are focused so much on the match, he will push in your leg like that. You call it knee jerking, or he will push your back. When your back is suddenly pushed, you realize that your neck jerks out. That is very dangerous. It can cause your neck to break. It is because your body was in a state of rest before your body was pushed. So when your body is pushed or your knee is pushed like that, your head feels reluctant to change that state of rest. Your body is going. Your head feels reluctant to change that state of rest. So it still wants to continue to be there. So while your body is going, your head is not going. That is when you feel that your neck jerks. And that is very painful. So these are some of the applications of Newton's first law of motion. Good. We look at Newton's second law of motion. Newton's second law of motion. The Newton's second law of motion. This law states that the rate of change of momentum of a body is proportional to the force applied to the body, and it takes place in the direction of the force. I'm taking it again. The rate of change of momentum of a body is proportional to the force applied, and it takes place in the direction of the force. So what is momentum? Momentum. We define momentum as the product of mass of a body and the velocity of the body. Momentum is the product of mass and velocity of the body. Anytime we multiply a mass by the velocity of the body, we get what we call momentum. So the rate of change of momentum, according to the second law, the Newton's second law, which gave rise to the formula for finding the force, which gave rise to the formula for finding net force or force. The Newton's second law is interpreted as this: that the force applied is proportional to the rate of change of momentum. Change in momentum, rate of change of momentum means change in momentum per time taken. So momentum, mv minus mu all over t. What is mv? Momentum after collision. What is mu? Momentum before collision. The u stands for the initial velocity. So we'll multiply the initial velocity by the mass. That will give us the initial momentum. We'll multiply the final velocity by the mass. That will give us the final momentum. So mv minus mu all over t is proportional to F. So when we remove these proportionalities, I will introduce a constant. F is equal to a constant K into bracket mv minus mu all over t. But this constant K was found by Newton to be 1. Because you know that 1 Newton is equal to 1 kilogram per meter squared. So for that matter, this constant K is equal to 1. Therefore, F is equal to mv minus mu all over t. This is the formula for force. Why? Let us, we have dealt with linear motion, so we know this. Let us factorize m out. If we factorize m out in this equation, let me write it here, we'll get this. F is equal to m into bracket v minus u all over t. Look at this. V minus u all over t. That is acceleration, right? Yes, that is acceleration. So in place of this, I can put acceleration there, and that will give me F is equal to ma. So from the Newton's second law of motion, we get the force F is equal to ma, which we refer to as net force on a body. Good. So this is what we deduced from the Newton's second law of motion. Applications of the Newton's second law of motion. If you haven't been to the stadium before, well, one day you go there. When you go there, observe this. High jumpers and pole vaulters are given foam mattress to land on. All right, they are given mattress to land on. Why? Because this high jumper jump into space. He's fallen under the force of gravity, so his velocity is increasing as he gets to the ground. This high jumper is going to hit the ground with a certain initial velocity, which is huge. The moment he hit the ground will not move, so his final velocity will become 0. What that means is that when the final velocity becomes 0, the change in momentum is going to become minus mu over t, which will produce the force in opposite direction because the change in momentum is negative now. So that will produce a force in opposite direction. Remember, in the Newton's second law of motion, the change in momentum must take place in the direction of the force. So if I write mv here, the change in momentum takes place in the direction of the force. So the force is positive, the change in momentum is positive. They are in the same direction. But in a situation whereby the change in momentum is negative, that is the situation of the high jumper that jumps and hits the ground, his momentum comes to 0 at once. And the force is in opposite direction, which is acted on the person that is hitting the ground. So because it takes small time for his momentum to change, why? Because he hit the ground. It takes very minute second for his momentum to change for his momentum to change. That small second will produce a very large force because the force is inversely proportional to the time. So that small time will produce a very large force which is acted back on him, and that causes him to sustain damage, to sustain injury. So in order for the high jumper or the pole vaulter not to sustain injury, what the athletes, the organizers do is that they provide this gentleman or this lady with a foam mattress, thick one like that, for him to land on. So when he lands on the mattress, it will take some time for the momentum to change. So the mattress will surge in and come out. And it will do that about 3 times. So whilst that is done, it is buying time for the momentum to change. Yes, even though the momentum will finally come to 0, yes. But because the time taken for the momentum to come to 0 is huge, what I mean, the force acting on him is less, it's very small. So when he hit the mattress, he will feel that yes, he has slammed it. But the force acting on him is not huge enough to cause damage to him. This is the reason why high jumpers and pole vaulters are provided with mattress to land on, because of the Newton's second law of motion. Else, death. Another application is, let's look at a car that collides with a tree. Of course, trees are stationary, Good. So a car that collides with a tree. Let's compare that one with a car that hits a wall. The wall breaks and the car enters. Which of these 2 cars will sustain damage? Of course, it is the car that hits the tree. Why? The tree is standing. The car bumps into the tree. Bang! It takes a very small second for the momentum of the car to change from that huge velocity to 0. So the impact on the car, because of that small time it takes for the momentum to change, the impact on the car is very huge. That caused the car to sustain much damage. Let's look at the other scenario. A car that hit a wall, the wall breaks. So the car hit the wall breaks, then the car moves small and then goes to stop. The car took some time for the momentum to change, to come back to 0. Because the car took some time, and the time is in proportion to the force that is acting on the car becomes less small. And the car does not sustain much damage. You get the principle? Good. The car does not sustain much damage. So these are some of the applications of the Newton's second law of motion. Good. Let's end there. There are so many examples that we can talk about, so many applications. Let's look at the Newton's third law of motion. The Newton's third law of motion. So the third law of motion. What does the Newton's third law of motion say? It states that to every action there is equal but opposite reaction. To every action there is equal but opposite reaction. What is the meaning of this? To every action there is equal but opposite reaction. Remember, the action and the reaction, they occur simultaneously. So once there is the action also takes place. You understand that? So if the action will have to take place, then later the reaction will come and take place. It wouldn't satisfy the Newton's law. For instance, somebody slaps me. Then I go and think about it. It pains me. At that point, it didn't pain me like that, but I go and walk around, then later it pains me, then I come back and slap the person. That is not action and reaction. Are equal opposite? No. The action didn't occur simultaneously. You understand what I'm saying? One of them happened. It took some time, then the other one happened. There was a thought through. That is not action and reaction being equal and opposite. A typical application or example of it is the firing of a gun. You see, when a gun is fired, let me use this thermometer as an example. When a gun is fired, the bullet moves out with a very high speed. The bullet speed, very high, multiplied by the mass, will give the bullet a certain momentum. The emphasis on the momentum, not the speed. Take note of it. That will give the bullet very high momentum to go. That is the action. According to the law, there has to be equal but opposite reaction. So the gun recoils backwards. Alright? The gun recoils backwards. So the recoiling of the gun with a small velocity. Why small velocity? Because the gun has a large mass. So the large mass of the gun multiplied by the small velocity will be equal to the high velocity of the bullet multiplied by the small mass of the bullet. I think it makes sense, right? That is the reason why you don't have to use the velocity to explain it, but you have to use the mass, the momentum to explain it. So what is the action here? The action is the bullet moving forward with a momentum that will produce equal but opposite momentum backwards, which is the gun recoiling. Another practical example is the firing of a rocket. You know, when a rocket is fired, a large mass of smoke comes out with very high speed. So that large mass of smoke coming out, which is the action, produces equal but opposite reaction. It produces equal but opposite reaction, which propels the rocket forward with very high speed. So the rocket being propelled forward is the reaction. The smoke coming out of the gun, coming out of the exhaust of the nozzle of the jet or the rocket is the action. Another practical example is the paddling of canoe. You know, when you paddle a canoe, you sweep the water out like that. Action. Equal but opposite reaction. The canoe moves forward. So action, reaction. Action, reaction. The two of them happen the same way. Whilst you sweep the water backwards, the canoe also move forward. It's not that you sweep the water backwards, then later the canoe move. The two of them happen simultaneously. I hope that is clear. Good. So these are the Newton's 3 laws of motion and the applications of the 3 laws of motion. So, subscribe to my YouTube channel, bjonline.com, so that anytime I post a video like this, you will be able to have it. And then tell your friends to watch it so that they can also learn something from it. Your comment on the Facebook page is also very important. The Facebook page is BJ's Physics Classroom. Your comment on the Facebook page is also very important. Remember that your comments will help me do a very good video. You know, look at 1 or 2 mistakes I did, and then I can correct them. I want to know the mistakes that went on, things that you don't like on the page, things that you don't like about the video, so that I can correct them and make a very good video for you. Thank you very much. Please subscribe to my YouTube channel. Let's continue. Now we look at momentum and collision. So we look at momentum. We have already said that momentum is the product of mass and velocity of a body. So the unit for momentum is kilogram meter per second. This is the unit for momentum. Good. So when we say change in momentum, that will give us final momentum minus initial momentum. So what is final momentum? The mass times the final velocity. Those of you that have done linear motion, when we write V, it's a conventional symbol. V stands for final velocity, U stands for initial velocity. So mv minus mu, that is the change in momentum. And the change in momentum must take place in the direction of the force. So when the change in momentum takes place in the direction of the force, that is according to Newton's second law of motion, then the change becomes positive. The moment the change becomes negative, then it means that the change in momentum is in opposite direction to the force. Good. Now, let us look at this. Impulse. There's another term we need to look at. Impulse. Now, when we say impulse, we define impulse as the product of the force and the time taken for the force to act. The product of force and the time taken for the force to act. So the unit for impulse is Newton second. Newton second. But you know that Newton is kilogram meter per second square. So multiply by second. This is raised to the power 1. This raised to the power minus 1. This one will take away one of these. That will give me kilogram meter per second. Look at the unit for impulse. Kilogram meter per second. Look at the unit for momentum. It means that momentum and impulse have some things in common. And what they have in common is the change in momentum is equal to impulse. How do we get it? Look at this. From the Newton's second law of motion, the force F is equal to mv minus mu all over t. So let me multiply through this equation by the time. That is going to give me Ft is equal to mv minus mu. What is Ft? Ft, impulse, I. Impulse, I. So Ft is I. What is mv minus mu? mv minus mu is change in momentum. It means that impulse can also be defined as change in momentum of a body. So the unit for impulse is the same as the unit for momentum. And they have the same dimension too. The dimension for impulse is the same as the dimension for momentum. Good. So one thing I need you to take note of is this equation and the fact that impulse is also equal to change in momentum and this equation. They may ask you to use these equations to solve some questions. If you have any question, you can send it to the WhatsApp page, BJ's Physics Classroom, the WhatsApp page, or you can post it. If you are not on the WhatsApp page, you can post it on the Facebook page. I will address the question for you the moment I see it. Thank you very much. Good. So, now we know that impulse is equal to change in momentum, mv minus mu. Now, this is a situation whereby both the initial velocity and the final velocity are in the same direction. In a situation whereby the initial velocity and the final velocity change direction, the impulse formula will change because velocity is a vector quantity. This is seen very well under rebound situation. What's a rebound situation? An object like this hit the ground and the object bounce off. So look at this. Bounce off, you understand? So in a rebound situation, the object, let's look at this scenario. This object moves down with a certain initial velocity. It hit the ground with a certain initial velocity u. Then when it hit the ground, it bounces off. It bounces off with another velocity v. Because the two velocities are not in the same direction, remember I have told you that for this formula to hold, the final velocity and the initial velocity must be in the same direction. In a situation whereby the two of them are in opposite directions, the u becomes negative. One of them is made negative, usually the u. So it becomes I is equal to mv minus into bracket minus mu. Then the I becomes equal to mv plus mu. So in a nutshell, in simple terms, change the impulse in a rebound situation, or in a situation whereby the initial velocity and the final velocity are not in the same direction. What you do is add the two momentums, the initial and the final, to get an impulse. Take note of that, it will help you a lot. Good. So that is one thing you need to take note of. Okay, so we look at collision. when two bodies collide, and that, collision here, we are looking at collision under linear momentum. So before we even go to the collision and the linear momentum, let's look at the law of conservation of momentum. The law of conservation of linear momentum states that the momentum before collision is equal to the momentum after collision, provided there is no external force. So in a system of colliding bodies, in a system of, I have two trolleys here. So in a system of colliding bodies, provided there is no external force acted upon them during the collision, their momentum before collision is equal to their momentum after collision. Good. So that is the law of conservation of momentum. The law of conservation of momentum. Now, the law of conservation of momentum states that m1, m2, moving velocity, u2, u1, this is before. So before they collided, right? After collision, the two of them move with velocities, m1, v1, m2, v2, they move with final velocity. This is after collision. According to the law of conservation of momentum, their momentum before collision, that is the sum or the algebraic sum of the momentum before collision, which is m1 u1 plus m2 u2, right? m1 u1 plus m2 u2, that is equal to m1 v1 plus m2 v2. So m1 u1 plus m2 u2, that is momentum before collision. That is equal to m1 v1 plus m2 v2, momentum after collision. Alright? Good. So this is the relation we get from the law of conservation of momentum. And momentum is always conserved in a system of linear collision. At your level, you're only supposed to know linear momentum. We also have angular momentum and then some other stuff, but for this particular topic, we are dealing with linear momentum. Good. So in our next discussion, we will look at this into details. We'll look at the types of collisions that we have. Then we'll look at how the momentum conservation principle is applied in those areas. Before we do that, let us try and understand some of the things that we have done, and then we deal with coefficient of restitution before. So the coefficient of restitution and then the collision will be dealt with under the next video. So let's look at this example. Let's look at this example. Example 1. A gun of mass 2,500 kilograms fires a bullet of mass 10 grams with speed 1,000 meters per second. Okay, 1,000 meters is too much, 1,000 meters. Let me make it with speed 200 meters per second. Find the recoil velocity of the gun. You know, this has been a past question before, but I didn't quote everything verbatim. I paraphrased it. So some of the values and the wordings have changed, alright? But the central idea is the same. The most important thing is the understanding. Good. So let's deal with this solution. Let's solve it. In the question, we have been given the mass of the gun. Let mg be the mass of the gun. That is 2,500 kilograms. Let the mass of the bullet be the mass of the bullet is 10 grams. It's 10 grams. So if I convert 10 grams to kilograms, that is going to give me 10 times 10 raised to the power minus 3 kilograms. And then, I divide by 1,000. So if I divide by 1,000, it will give me this one. Then the velocity of the bullet, that is 200 meters per second. Now we want the velocity of the gun. The velocity of the gun. There are two ways I can do this. I can use the momentum conservation principle to do it. I can use the Newton's second law to do it. Or I can use the application of the Newton's third law. The Newton's third law will make it easier for us. Alright? The Newton's third law will make it easier for us. So let me use the Newton's third law of motion. According to Newton's third law of motion, to every action there is equal but opposite reaction. So action and reaction are equal and opposite. What is the action? The momentum of the bullet, that is the mass of the bullet, times the velocity of the bullet. That's the momentum of the bullet. That is equal to the negative, because they are in opposite directions. That is equal to the negative of the mass of the gun and the velocity of the gun. What are we looking for? The velocity of the gun. So we say that Vg, which is the velocity of the gun, is equal to the mass of the bullet, 2,500 times the velocity, the mass of the bullet, sorry. The mass of the bullet is not 2,000, that's the mass of the gun. The mass of the bullet is 10 times 10 raised to the power minus 3 times 200 divided by 2500. Good. So when we simplify this, it will give us this times this. That is going to give me 2 times 10 raised to the power 3. 1, 2, 3 zeros. Times 10 raised to the power minus 3. This one. All over 2.5 times 10 raised to the power. Okay, all over. Let me make it, 2.5 times 10 raised to the power. 2.5 times 10 raised to the power 3. 1, 2, 3. Good. So this one will go over with this, and this will give us 2 divided by 2.5 times 10 raised to the power 3. Alright? Good. So if you have a calculator with you, punch this one. 2 divided by 2.5. 2 divided by 2.5. Okay. So this can also be written as 2 divided by 2.5 times 10 raised to the power negative 3 meters per second. I don't have a calculator with me. And for the sake of time, I don't want to go through the division of this one. So pick your calculator and divide this so that you get the final answer. So this is how we go through the question using the application of the Newton's third law of motion. Good. So let me give you assignment. I'm running out of space on the camera. So let me give you assignment assignment. A ball of mass 200 grams is released from height 40 meters above the ground. 40 meters above the ground. If the ball rebounds to a height of 28 meters, find the impulse received by the ground. Find the impulse received by the ground. Good. So we have this as assignment. A ball of mass 200 grams is released from height 40 meters above the ground. If the ball rebounds to a height of 28 meters, find the impulse received by the ground. Take it to bracket. J is equal to 10 meters per second squared. So, thank you very much for being part of the show. It's been your man BJ. Please subscribe to my YouTube channel so that anytime I post a video, you'll be able to get it. And remember to always wear your nose mask anytime you're in public to safeguard yourself from COVID-19. Sanitize your hands. Make sure you follow all the protocols that have been outlined by the state so that we can all stay safe. So till we meet again to continue with this episode of linear momentum and Newton's laws of motion and linear momentum. Thank you very much and stay blessed. Bye-bye.